To make it clever.
So we're going to be starting the quiz with Mr. Vincent Germain to my left. He's currently working on a thesis on gravitational waves at the Annecy particle physics lab. So without further ado, I'll pass the mic over. Hope you enjoy it and be polite and cordial with the people.
So thank you. So I'm French, so if sometimes my English is really bad, don't hesitate to ask me questions or repeat, okay? So, hi everyone. So my name is Vincent, and I'm not going to talk to you really about gravitational waves, but more about space-time to begin with. And then Tom will do the talking about gravitational waves more specifically, okay? So, okay. So we have a sponsor also. So who supports us this is our laboratory, so lab. We are supported by the CNRS and university. We are working on Virgo, and the way we get beer is doing talk like this. So space-time. Space is 3 dimension, okay, you can explain movement by 3 directions. And time is 1 direction, so forward or backward. Backward, more difficult, but 1 direction. And we consider space-time as a whole, so we say it's 4 dimension, okay? And there is 2 important things to know about space-time. Is that the mass will distort the space-time, and this deformation will influence the mass. So if there is a kind of a hole in the space-time, the mass will go in the hole. This is what is shown with this picture. So this is a 2-dimension representation. The grid is a kind of a space-time, and you can see that the Earth is a small mass, so you have a small deformation, and the Sun is more massive, so you have a bigger curvature. Okay? What is gravity? You have a hole created by a mass, and everything falls toward this point. Okay? So this is why everyone is falling toward the Earth. Why you have the orbits of the Moon, and you can explain it also with the Sun, which creates a bigger deformation than the Earth is orbiting around the Sun. Okay? So if you want to escape gravity, if you want to escape Earth, for instance, if you take a rock and you throw it in the sky, it will fall back on the Earth unless you are really strong and you launch it with a speed of more than 40,000 km per hour. Just for you to know, the world record in baseball is less than 200. So. But the Earth actually is not that massive. I told you there is the Sun and more massive star with a bigger gravity, a stronger gravity. So we will look at these stars now. Okay. So we are going to separate stars in 2 categories: the low mass and the high masses, because they evolve in a different way. The Sun is a low-mass star, actually, and it will evolve as a red giant, so it's just going to expand in the end of its life, in 4 billion years, and it becomes, at the end of its life, a white dwarf and will slowly be frozen and die slowly. And massive stars, which are more than 8 times the mass of the Sun, will go as a supergiant, and then we have a really interesting phase, which is a supernova. It's when a star explodes. So why does this happen? Actually, a star needs fuel, and fuel is the hydrogen in the universe. So it will create a nuclear reaction, and all this explosion will create a force which push on the outside, so it's a radiation pressure, and this is balanced by gravity, which attracts everything to the middle. So you have an equilibrium between these two forces, and the supernova is when you don't have hydrogen. Okay. Whoa. It's supposed to start. Okay. Oh. Okay. Okay. So the supernova happens when there is not enough hydrogen to balance the gravity, so everything just collapses, and it goes on the earth of the stars, which is super dense, and there's like a rebound, and everything explodes. And the only thing that remains, it's the core of the star itself, and this core is super dense and with a high mass. And depending on the mass of the core, you can have two possibilities. Either it's become a neutron star, so if the core is 1 to 3 times the mass of the sun, or a black hole if it's from 3 to 50 or 100 solar masses. A neutron star is actually a super incredibly massive star, but with a really low radius. It's a really a small object. So if you take a teaspoon of the matter of a neutron star, it's more than a billion tons. It's 900 times the weight of the Pyramid of Giza. Just a teaspoon. So the gravity on the surface, you can imagine it's really big. It's 200 billion times the Earth gravity. So you can stand and you'll be crushed and die, and okay? Don't do it. And the escape velocity, if you are on this neutron star, it's a third of the speed of the light. Okay, if you want to escape this gravity. And I told you it's really massive, so it's more than the mass of the sun, but it's really small because for the sun, which is 1 solar mass, you have a radius of 700,000 kilometers. A neutron star of the same mass is 12 kilometers. Okay, so it's more or less Chamonix. And yeah, if you compare, it's just a dot compared to the sun. For a black hole, it's more or less the same size. It can vary depending on the mass, but more or less same scale. And it's more massive, so the escape velocity is above c. It's more than the speed of the light. So even the light can't escape. This is why it's a black hole, because everything is trapped in it. So what happens in a black hole stays in a black hole. So again, if you compare the size between the sun and the black hole, it's just a dot, and it's really small if you imagine at the size of the universe. Okay, so don't fall into a black hole, because there is a special thing, which is spaghettification. Actually, you have to imagine that the gravity is so strong close to a black hole that the gravity that you feel on your feet will be much stronger than on your head. So you will be just pulled apart and stretch, and you die again. So don't do it. Okay, so just a quick summary. The distortion on the space-time according to different objects. The sun, so low mass, you need 0.2% of the speed of the light to escape. A neutron star, you need a third of the speed of the light, and you have a bigger distortion, okay? And the black hole is more than c, and here you have a really strong gravity and really big distortion. So now imagine that you take two of these objects, so like two black holes, and you make them orbit around one each other, okay, one another. Then you can imagine a lake, which is a space-time, and these two objects will create waves like this, because you have a system with an asymmetric mass. If you move your arm, you create gravitational waves. Okay? It's just that the amplitude will be really small, and we will not be able to detect them. Because even with black holes of several solar masses, it's really difficult for us. So we need this high mass to be detectable on Earth, and they propagate through space at the speed of the light. And nothing can stop them, actually, because it's a deformation of the space-time itself. And after this, we have a small break, and then Tom will explain you better what is gravitational waves and how we study them. Okay, so thank you.
This is Thomas Adams. He's going to blow your mind now. Have fun.
So I'm going to talk about gravitational waves. These were first predicted by Einstein in 1916, which is in the quiz. I'm glad I got that right. And he actually thought they'd never be detected because, as Vincent said, they're incredibly weak. But actually, yes, he actually thought himself, even though he predicted their existence, that they wouldn't be detected. So until last year, the only evidence we had that they existed was indirect. This was done with observations of binary neutron stars, such as the Holtz-Taylor pulsar, which is a binary system of 2 neutron stars discovered in 1974. So after 40 years of observation, we have these results here, which are really exciting. So the red dots are the observations, which are the so this binary orbits, it emits gravitational waves, and this means the system loses energy. So the two objects in the binary become closer together, and their orbital period increases. So this shows the change of the orbital period over time, 40 years on the x-axis. And you see that there's the red dots, which are the observations, and the blue line is the prediction as predicted with general relativity. Okay, so that's the prediction from general relativity, which is obviously in very good agreement, unlike me in this laptop, until now. So last year, we made the first ever detection of gravitational waves. This is an incredibly important discovery. You may have heard it in the news. These are a few of the front pages that were reported around the world. It was really exciting in the scientific community. There was a lot of interest in the public as well. So I'm going to show a short video, hopefully with sound, but I can't guarantee it, from the press release that was given in February the 11th this year in Washington, DC, by the head of the LIGO collaboration. He says, it won't be the same if I say it, but he says, we detected gravitational waves, we did it. And everybody claps, and it's great. And there we go, that's better. So, it was kind of like that. But in America. And there was also another announcement, which was in Italy, detecting having Pisa. And there was also an announcement in Paris, which me and Vincent had the privilege to attend. So this was a confirmation of a prediction made by Einstein 100 years ago. I'm going to give a brief outline of this event now, but for the interested reader, please search observation of gravitational waves in Google or your favourite search engine. It's the first result, there's a PDF, it's open to the public because it's an important result and everybody should be able to see what their tax dollars go towards. This is what's paid by tax funding. So the event is called GW 150914, and that is a very interesting name just from the date. There's no other, it's not interesting. This is how we're going to name gravitational waves. This is the first one we've had, and it's a very confident detection. So without the gravitational wave in our data, just looking at the noise in our detectors, we would expect an event of the same loudness in 200,000 years. So it's an incredibly rare event if it's noise, but we're confident that it is a detection of a real signal. And the source of this was a merger of two stellar mass black holes. So what actually happened was these two black holes orbit each other. They emit gravitational waves like the Hulse-Taylor pulsar. Their orbit becomes closer together, and then they merge, creating a strong chirp of gravitational waves. And that leaves a single black hole, which will then relax over time into a sphere. And the whole time it's going to be emitting gravitational waves. So the prediction from general relativity is given in red, and the observed signal is given in grey. You can't see much separation, which is a good thing. So there's strong agreement. And this is the actual signal in our two detectors with sound now, which is great. So these are the two of the detectors which we have, which are in America. And this is the data. So you can actually see the gravitational wave signal as it increases in frequency as the two objects become closer together. The amplitude increases as well, having a chirp, and then there's a single black hole which will ring down afterwards. So this is time on the X, frequency on the Y, and our detectors operate in the same frequency band as the human hearing. So you can actually just take the signal and transform it into an audio file, which is what we heard in the background. So I'll play it again, and it's going to play the signal twice, and then a frequency shifted version of the signal, which is a little bit higher in frequency because it's easy to hear. So this is the sound of two black holes, 30 times the mass of the sun, colliding in the most energetic event that we have ever discovered. It doesn't sound like this. So this is the heaviest stellar mass black hole that has ever been observed, the one that was after the merger, 60 times the mass of the sun. This is also the first time that we've ever actually observed binary black holes in nature, and we have observed them merging together, which is something we weren't sure until now whether that would happen in the age of the universe. And this is also a great confirmation of Einstein's theory of general relativity. Now the amount of energy in that event, I said it was the most energetic event we've ever observed, is actually the same amount of energy in that small signal over a fraction of a second was the same as all of the light that's been emitted by all of the stars in our galaxy in 500 years, which is incredible. It's a lot of energy in gravitational waves, but they're very, very quiet. So the black hole that's 60 solar masses looks like this on a set of scales. This is 60 times the sun, and there's the black hole. It looks impressively heavy, but that's an over-exaggeration because that is actually a lot bigger than the real black hole is. The actual diameter of the black hole is around 400 kilometers, which is about the size of Iceland. So imagine 60 times the mass of the sun compressed into a sphere the size of Iceland. Pretty dense. So what the hell are gravitational waves? We've been talking about them. I'm going to go over it again because it's hard to get your head around if you've not heard about this before, and it's a good excuse to show a nice animation. So here's the binary black hole that we observed. The two black holes orbiting each other in the last tenth of a second before they merge. They're becoming closer together as they emit gravitational waves. Now it's going to slow down for the cinematic effect. And they're going to merge together, creating a strong burst of gravitational waves, which is shown in the the two-dimensional space-time, which is this coloured plane. And then there's a single black hole with 60 circles black hole left afterwards. And this is the gravitational waves propagating out from the source. So as these gravitational waves move through space, they move at the speed of light. And the way that gravitational waves can be detected is the way that they interact with matter. So imagine a gravitational wave moving out of the board, and we have a ring of particles on the board, or just in front of the board. You have to use your imaginations here. And gravitational wave will change the distance between the particles. It won't actually move the particles, but because it's a stretching and squeezing of space-time itself, it will actually change the distance between the particles. So that circle isn't changing size. Those particles aren't moving, the circle isn't moving, but the size or the position between the particles is changing in the X and Y, as you can see. But that's greatly exaggerated. The actual effect is really small. And that's a good thing, because here's another animation of gravitational waves arriving at Earth. And the effect they'd have on it. Which also is not to scale. Which is a good thing, because that would not have been good, but it would have made our jobs a lot easier, because they would have been a lot easier to detect. So, the way that we can make a measurement of gravitational waves is to take a length of space-time and measure its length, because that length will change when a gravitational wave passes. But that change is really small, as I said. But if we imagine a meter rule, we can, for scale, think what the change from a gravitational wave passing this meter rule would be. And it's smaller than the thickness of the St. Common, which is about a millimeter. It's even smaller than the width of a human hair, which is 10 microns, or 10 to the minus 5 meters. It's even smaller than the width of the DNA, which is a nanometer, and the radius of a helium atom. 10 to minus 21 meters or less over 1 meter, which is this number, which is very long for it's quite impressive if you write all the zeros. So that is the same as well, it's a brilliant the size of the width of a proton, and it's the same relative size as the distance between our nearest star and the sun, which is 10 million kilometers, and the width of a human hair, which is 10 microns. So that's a ridiculously big difference, which is obviously quite a challenge to detect, and we require very, very sensitive detectors. So how the hell do we do that? Well, the current most sensitive detectors we have are called gravitational wave laser interferometers, which use some of the strongest and largest vacuums on the Earth. What we do is we take two lengths of space and we compare their length. Because they're perpendicular, like a ring, we're basically measuring essentially vertically and horizontally, so the effect is differential. One arm will get longer as the gravitational wave passes, the other arm will get shorter. It doubles our signal, which is useful in this case because it's really, really small. And these detectors are sensitive enough to detect gravitational waves, as we proved last year when we detected them. So what happens in this is we have a laser which comes into a partially reflective mirror called a beam splitter, which lets half of the light through and half of the light is reflected. This light is then sent along two perpendicular arms in vacuum, and then reflected by mirrors at the end, recombined with the beam splitter, and output to a photodiode where we can measure a signal. And this gives us a very, very sensitive measure of the relative length of these two arms, which is how we're going to detect gravitational waves more. We've already done one. I'm kind of in the mindset of saying we're going to detect, because this is the first public presentation I've given since the detection, which is amazing. So it's different. Spend 6 years and then finally get it. So this is the effect of a gravitational wave coming from above onto the detector. You see the arms changing length. They're not moving, they're just changing length. And that has an effect on the output, which is just the interference of the light from the two arms, which we use as a measure of the gravitational waves. But this is a very, very simplified version of the detector. The actual detectors are a lot more complicated and a lot more interesting. So here's a few pictures in collage to make it extra confusing. You're not meant to take anything away from this, it's just meant to look sciencey. So there's mirrors and there's vacuum and there's people working on it in masks. It's quite impressive, trust me. So we have a network of these detectors all over the planet. We have 2 in America called LIGO, which I'll give more information in a minute. There's another detector in Germany called GEO, which I used to work on. And then there's the Virgo, which these 3 detectors are all operational at the moment. And then there's 2 detectors which are currently under construction called Virgo in Italy and Kagura in Japan. We work for Virgo because it's Italian, French and Netherlands collaboration. And there's also a detector planned to be installed in India in the future. So until last year, there were a lot of observing runs that we did over the last 5 or 6 years with no detections. Because the detectors were in a state where they weren't as sensitive and they were in a sense developing technologies which required long periods of actual observing. And then the detectors were switched off in 2010 and 2011 for 4 years for a period of upgrades where we would expect an improvement in sensitivity around a factor of 10. So through this period the GEO detector remained in case anything extraordinary happened, like the sun exploded. Then we could detect the gravitational waves from that. But the LIGO detectors came online last year and they made the first detection of gravitational waves. They are in Hanford, Washington State, and Livingston, Louisiana. One's in a desert, one's in a swamp. And they are 4-kilometer long arms. So these arms are incredibly long, and in fact these are the largest vacuums that we've made on Earth, because they're a 4-kilometer long arm continual vacuum. Very impressive. The Virgo detector in Italy is near Pisa. It has 3-kilometer long arms, and it isn't online yet, but it will be coming online later this year. I might be biased because I'm in the Virgo collaboration, but I think it's the most beautiful detector. We have mountains, we've got nice looking vacuum tubes and bottle covers. It's in Italy, which is good. And then in the future we have Kagura, which is the instrument which is being developed in Tokyo, underground in the Kamioka mine. It's expected to come online in 2018. And in India we have an instrument planned for the future, which should be coming online after 2022, or there and thereabouts. And in the future there are plans to actually put an instrument in space. But that's just proposed, and the launch date would be 2034, so that's a bit more in the future. But that would be interesting. So these instruments give us data, but you can't just look at that with your eye and find these signals, because that's really difficult, even with these incredibly sensitive detectors. We have to use software to do that for us, and there are two different ways that you can do this, which I'll divide. Is online, where we have a very strong emphasis on detecting gravitational waves as soon as possible. And the idea of this is that if we can detect them within a few minutes, we can then send that information to other astronomers who can then perform observations with electromagnetic waves like infrared or gamma rays or visible light, and they can follow up and maybe see something that they wouldn't have seen otherwise, because we've alerted them to it before it's actually been visible in the way they normally look. And this allows us to learn more about objects if we can see them with multiple messengers, like gravitational waves and light at the same time. And then there's also offline analyses, which are much more sensitive, and they can make a much more confident detection of these events. But they're more computationally expensive and slow, so they're archival, they're just performed after the fact. So the online analyses perform, they give you just timing information because you will receive a signal in the detector. But none of our detectors have any directionality. They're essentially like a microphone. The microphone doesn't discern which way the signal is coming from, it just picks it up, unlike a telescope which you point in a particular direction. So what we have to do is detect a signal in multiple detectors and then just do triangulation between these, which gives us a source location on the sky, a sky position which we can give with the time to the astronomers to follow up. So why are we interested in gravitational waves? Why are they exciting? I hope you're excited, because I am. Well, we see the world through visible light, which is great, but there's a lot more electromagnetic waves out there that we can't see with our eyes. And this makes up the electromagnetic spectrum, and since discovering these other wavelengths that we can see the universe with, such as radio waves, microwaves, ultraviolet, gamma rays, for example, X-rays, they've given us a better understanding of the universe, and they've also enhanced our lives in a lot of ways. I'm sure you can think of useful uses for things like X-rays, for example. They're kind of helpful. But they totally changed the way that we see the universe. So this is this night sky as seen in visible light. You can see the galactic plane, which is made up of just stars. And then in the background you can see other sources, which are other galaxies outside of our own. But there's a lot of other stuff in the way that you can't see through, like dust and gas. But this is just the visible. In fact, if you look in the microwaves, that is what actually is emitting the light. So here you can see in the galactic plane the dust and the gas in our galaxy, and then in the out of the orbital plane you can see the remnant radiation from the Big Bang. This is the low energy, long wavelength regime. If you go to the other end of the spectrum in gamma rays, the high energy regime, you see a totally different view of the galaxy and the universe. Here we're seeing high energy systems like black holes and neutron stars, supernovae, and things called gamma ray bursts, which we believe are the merger of two neutron stars colliding, which create incredibly strong bursts of gamma rays. They're the strongest electromagnetic sources that we observe. So you can think of the analogy that electromagnetic waves and gravitational waves have two different ways to view the universe. They have two different complementary spectra. Electromagnetic waves let us see the universe. Gravitational waves essentially let us hear the universe. But you can't actually hear the universe because there's no sound in space. So the sky for gravitational waves, we've got one source, we're going to get more in the future. And that's going to help us to fill up this view of the sky and help us to understand more about our universe. But besides just detecting gravitational waves, what other things can we do that are exciting? Well, in astronomy, this, as I said before, allows us to alert astronomers to things before they happen, such as supernova. We only see remnants from supernova after they've happened currently. But with gravitational waves, you can actually point your telescope in the sky and see a supernova happen, which has never happened. It allows us to observe the sources we expect, like binary neutron stars and binary black holes. And as I said, we expect gamma ray bursts to be caused by binary neutron stars, but we're not sure. This could be the way that we prove that they are or aren't. And also there's a search for the unknown, because every time we've looked in different spectra from the electromagnetic spectrum, we found things that we didn't expect, because hindsight's a great thing. You think you know everything, but at the time you don't know what you're going to find. Besides astronomy, there's also some fundamental physics we can do, like testing general relativity in strong gravitational fields, like near black holes. We can confirm gravitational waves do actually travel at the speed of light as we expect. This is also a way to see into the really early universe, like the Big Bang, because in the very early universe it was opaque and you couldn't see through the material that made up the universe until about 300,000 years after the Big Bang, whereas gravitational waves will let you see much closer because, as Vincent said, they're not stopped by anything. They'll pass through material because they're not interacting with it, it's just space actually itself. that carries the signal. And it's also an independent measure for the age of the universe. So this is just the beginning. The next observing period will start this year, which will now include Virgo detector and the 2 LIGO detectors. So we hope to make lots of new and exciting discoveries. So stay tuned for more. Thanks for listening. Have you got any questions?